we've talked about over the last couple of days about energy, kinetic energy, potential energy, work, power. Is it true that energy cannot be created or destroyed?
Yes.
Yeah, it's the first law of conservation of energy. Basically, it cannot be created or destroyed, but it can be changed from one form to another. What the heck does that mean?
Potential to...
What?
Potential to...
In other words, rolling down a ramp would be potential energy to kinetic energy?
Yeah.
How about you eating your breakfast this morning? There was chemical energy in that. It transformed to another form of chemical energy. And now you're talking, you're thinking, you're breathing. All of those are different forms of energy. Questions? And this is just basically talking about how the transformations can be all kinds of different ones, where it goes from potential, kinetic, thermal to chemical, electrical, light, pressure, and nuclear, which we'll talk about in a little bit. Different forms of energy that it can be involved with. Mechanical energy. On the skateboard park, remember off to the right it says mechanical energy. Mechanical energy is both the potential and the kinetic. That's basically how machines or how things move about. Another form is radiant. The lights up here. That's a form of radiant energy. Is radiant energy dangerous? It can be, depending on the type of energy. For example, X-rays, gamma rays, are they dangerous? Yeah, they can damage your DNA. UV radiation, can that be damaging? But is it needed? Without it, you do not have vitamin D. Your body normally. How about heat? Is it damaging? Too much of it is, but just by itself, it's a good thing. How about microwaves?
Yeah.
Absolutely, positively, almost 100% no. They have less energy than heat, except for about 5 wavelengths. 5 wavelengths of microwaves are the same size as water molecules. And we'll learn about this later on, but I'm going to tell you now. You guys remember when you were little kids? And you got on a little swing, and what did you say to your dad? Daddy, Daddy, swing me! Why I heard that a lot when I was in the park with Wesley and Rosie. And so I would push Wesley, and he'd come back, and I'd push him at the same when he's coming back, right? And what would he do? He'd go fly. No, I would not do that, because what would Mama Bear do to me? My wife would kill me. And so what I did is, at the same rate he was going, I would be pushing him. And so I keep on doing it, and he'd go faster and faster and faster. That's what happens with microwave ovens. The frequency of light is the same as water molecules. And so when it goes by the water molecule, it pushes it and pushes it and pushes it, making it bounce back and forth faster and faster and faster. That's why it heats up the water. These things that we call our cell phones work on microwaves.
What do you mean, work on microwaves?
They send their signal using microwaves. The signal goes through the walls, go through most things, because these walls are invisible to microwaves. And so they pass through very easily. As long as you are in sight of a microwave tower. Questions on that? You got radio waves. Are radio waves damaging? Not at all. Okay, there are different types of energy. How about nuclear? Nuclear energy is where there's 2 types. There's fission and fusion. Fission is what we use. We get a little bit of energy out of it when we split an atom. Okay, we split it from one form to another. Our sun does a different type of nuclear energy, and that's called fusion, where it started out with all hydrogens. All the hydrogens form together, and that's how every atom we have in our bodies formed, was in stars. And so you're made up of stars. That's how a star was born. Electrical energy is derived from either chemical energy, radiant energy, other types of energy that are transformed into electricity. And we'll be talking about that more in a second. Plus, we're going to have an entire unit on it. We're going to hit it hard and heavy right after we get back from winter break. Why? Because we're going to be talking about also going into climate change at that point in time. How that's related. This is how electrical energy, most types of electrical energy that we use is formed. What we do is we take some chemical like methane, natural gas, coal, and we burn it. When we burn it with heat energy, that goes and heats up water. Almost 100% of the time we use water to heat it up. And when that happens, it forms steam. When it forms steam, it pushes a turbine. And so the hot steam goes in here and causes this thing to spin. And that thing in there has what's called a turbine. That turbine has magnets in it. And those magnets, when they spin around a piece of wire, they cause electrons to form. All of you have experienced this. You just didn't know it. Have you ever, I know you've done this. You know when you drive up to a stoplight and you go over these little circles in the road? Those little circles, when I was growing up, we used to thought it was done by weight. And the standing joke at that point in time is, your mama's so fat that when she walks across the street, she's going to turn the traffic light. That's not how it works. What happens is your car is in a magnetic field. Therefore, it has a north and a south. When it goes over that coil of wire, it causes the electrons in there to flow. That sends a signal to the light to say, switch. Something is give me a charge, and therefore I need to switch so that this stop happening. Are there questions? There are other forms of electricity than that. For example, I just put on solar panels on my house. Why? Because I don't want to have to keep on paying Glendale Water and Power so much money. There are other types that work a little bit different. This is one of them. Hydropower works by taking potential energy and forming it into kinetic energy. Look at the picture there. At your tables, discuss the two ways that potential energy becomes kinetic energy. This way, behind a dam, or coming down off the mountain. Go, talk. Come on, guys, talk. Table 4, talk to each other. She does very well most of the time. Just keeping her cool. 5, 4, 3, 2, 1. Table 7. What happens on the dam?
The water from the reservoir goes into the turbine, and I get the water.
But why does it go there?
Because it's at the bottom. And
But so what does that have to do with? Remember, this is a physics class. When you answer a question on a test for a physics test, do you want to put it in physics terms, or you want to say the way an English person would say it? Put it in physics terms. Why does it push it through? Okay, what was I asking about? Potential energy and kinetic energy. So how is potential energy and kinetic energy? What you said is 100% correct. But how is that related to potential energy and kinetic?
well, it's potential because it's at the very top, and it makes its way to the bottom.
So potential energy pushes down on here.
And then it turns into kinetic energy.
That kinetic energy goes through here and pushes the turbine. And that turbine spins because it flows by. Sort of like when you're blowing on the little fan you use. It goes by that, and that causes the turbine. How about going Anyone have anything to add to that? How about when it comes down the mountain? How is that related to potential and kinetic? Table 9 or 10? Any ideas on how that goes potential to kinetic?
Starts at the top and then moves down.
Okay, so what is it at the top?
Potential energy.
So up here is potential energy, and as it's coming down is kinetic energy. Very good. But guess what? That's a new type of energy use that's really was started in Switzerland and Sweden. What they have is they have great big huge tall mountains, and they've got a corkscrew. And what they've done is sort of like a screw that you put into the wall, and it's basically goes like that. And as the water goes by it, it causes it to turn. When it turns, it causes the magnets associated with it to turn around little coils of wire, and that causes electricity. But guess what? There's another place that you can use that. There are places like in Newfoundland where they've got tides. In Newfoundland, there are places where the tides come into the bays where the water during a 6-hour period will go from right here down where my feet is all the way up to the ceiling back here. As it's coming in, is that a lot of kinetic energy coming in? Would it be able to push a turbine? Yeah. Not just, and then when it goes out 6 hours later, it do the same thing. Come back in to 6 hours later. And so every 6 hours they have another source of renewable energy that they don't have to pollute the atmosphere. Any questions on that? Okay. But what does that have to do with simple machines? A simple machine is something to make our life easier. However, with a simple machine, do you still have to do the same amount of work? Yes. In these, the amount of work you do is the same, whether you're doing the work or the machine. The difference between it is you or I am doing the input. The machine is giving you something out of your work. Does everyone follow the difference between the two? You have to make sure you understand the difference between input and output. Input is what I do, or what you as I. Okay, all of you say I. I. Input. Okay, output is what the machine does, gives you out of it. So, for example, this biker is putting in force right here. When he does that, he gets these big wheels to move him forward. So work in is equal to work out. Notice where you have for us, it's very, very small amount of force being put in, but we have to do it over a long distance. Contrary to that, the machine is producing a lot of force, but over a small distance. Best example would be levers and tire jacks. So if I take a tire jack and putting away your cell phone, if I take a tire jack, pretend I have a tire jack, this right here. Have any of you had to watch or change tires? Okay, who has? When you do that, did you have the ones that go where you spin them, or the ones where you take the tire jack and go? Okay. What you do with this type of tire jack is you put it underneath the car. Now, how many of you are able to lift a car? Not many of us. I know you, yeah. But what we do with the tire jack is we put it underneath the car so it's snug, and then we take this long arm and we apply a small force and cause this to go maybe a meter down. When we go down that meter, with the jack, it may go up a centimeter. And so, say we push down with 10 newtons of force, 1 meter, it goes up 1 centimeter, not with 10 newtons of force, but 1,000 newtons of force. Would that be enough to start lifting the car? And you do that over and over and over again until it's gone up high enough so that you can take off the tire. Now, when you take off the tire back there, do you wait till the car is up in the air before you loosen the screws? Loosen the bolts? No. You loosen the bolts when it's up off the ground a little bit, but it's still the tires are still touching the ground. Why? Otherwise, when you try turning the bolts, the whole wheel is going to spin, and you won't be able to do it. So you just start removing them. Then you finish pulling it up. Remove remove the bolts. Now, very important. When you take the nuts off, you want to put them someplace safe. I'm talking from personal experience. My dad one time was changing the tire. He put them in the hubcap. And then he got up and he stepped on the hubcap. Where did all the nuts go? About 10 to 15, yeah. So we spent the next half hour, 45 minutes trying to find the hubcap, the nuts. Questions on that? Does everyone follow how the long distance, small amount of force led to a small distance but huge amount of force? The two of them are equal. We have different types of machines. We're going to talk about some of them. This one right here, the gears, you'd have that in cars, you have it in bicycles. The screw, putting something into the wall. Not many of us would be able to push that in. The pulley system, we're going to be playing with that on Monday. The wheel and axle, that's what happens in the car. And we'll actually be dealing with that a little bit tomorrow. The ramp, on Friday we're going to be playing with ramps, trying to figure out how they work. And then the lever. I love talking about the lever. With the lever, you've got three parts of it. You've got the input arm, you got the output arm, and you've got the fulcrum. The fulcrum is where it balances, the teeter-totter. The input force is over here. The output force is the opposite side. That's what goes underneath the car. And there's three types. There are three types. One that would be comparable to the changing the tire would be type 1. You don't need to know the different types. I'm just telling you about them. One of them would be like the pliers, where you have the relatively long arm over here, where you apply some force, and it magnifies the force over here because it's a shorter distance. And again, the force times distance is equal to the force times distance. What's a little bit weird is with the wheelbarrow. Here, the input force and the output force are on the same side of the fulcrum. Okay? But again, this one's farther out than the output. The input is farther out than the input. The one that's really weird is your arm. Because if we take my arm, for example, and we look at it, my arm is what? About 50 centimeters long. And where the fulcrum is my elbow. My elbow right here. And where the muscle attaches is about 2 centimeters from the elbow. That means that if I'm lifting, for example, 50 pounds curls, I have to do a lot more force by my biceps. Why? Because this distance is longer than this distance. The output distance in this case is bigger than the input distance. Doing the calculations, if I'm lifting 50 pounds, if I were to rip off the bone, the muscle off the bone, I don't suggest it. That's why I have this scar right here. Okay, 90% was. So if I were able to take that tendon and attach it to weights, instead of just being able to lift 50 pounds, I would have been able to lift somewhere between 600 and 700 pounds with just the bicep by itself. So what's the advantage of that? Evolution-wise, what is the advantage of having these long things out here? Anyone have any ideas? Yeah? Sports. Why? So you can throw balls. Otherwise you can't do it. How about way back when? Way back in the day, we slithered on the ground like a snake. When our arms got longer, we could go faster because we were away from the ground. Was it also advantageous if we wanted to fly? Or if we wanted to make sure that bear that was over in the woods 20 feet away didn't come any closer to us, so we could pick up a rock and throw it at it? Because I don't like bears eating me. Most of us don't like that either. Okay? That would not be fun. And so it was advantageous to have a backwards lever, one that works backwards than most machines. Now, the mechanical advantage, what the heck is mechanical advantage? If on this machine I only have to put 10 newtons of force, but I get 1,000 newtons out of it, 1,000 over 10 means I have a mechanical advantage of 100. It just, basically, you don't have to do the math. It just means you get more out of it than you put in. More force out of it than what you put in because you're going a longer distance. Another type is the ramp. This is similar to what we're going to be doing in class tomorrow. And what that means is what we're going to do is we're going to take chairs and we're going to put the chair at a certain height. Okay? We are going to be taking a cart and bringing it up to this potential energy. And the work we're going to be doing is changing the potential energy of the cart by using a ramp. If I have this length of ramp, I'm going to be applying a force over this distance from my arm down to there. That force times distance should be equal to the change in potential energy of just picking it up that distance. If I move it on the chair, so it's like this, the potential energy change is the same. So you just go up to this place right here. So you'd be measuring this distance here and the force you would have to apply to make it go up here. Then you do it, please don't, no more slivers. You go up here and measure it up here and applying a force this distance. What's going to happen to the forces as you decrease the distance? That's what you're going to find out tomorrow. Questions? Okay, another type of machine is a pulley. I love pulleys. That's the lab we're going to be doing Monday. If I have a type of pulley that has two ropes on it, this is 100 newtons. Each one of these takes half of the weight. And so because of that, because it takes half the weight, it means that it's going to have to pull twice as much. Well, let's try to look at it logically. If we want to lift this thing 1 meter, how much do I have to shorten that rope? 1 meter. How much do I have to shorten the other rope? 1 meter. That means I have to shorten both ropes how much? 2 meters. That's how it works. 2 meters times half the force gives me the same amount of work. However, that makes it so that we could pick an engine out of a car because we're using a pulley. Now, we have different types of pulleys. Here we have force supports. We have all kinds of different supports. But, just on the off case that you may be asked, hint, hint. Did everyone catch that? If I were to happen to ask you someplace how to draw different types of pulleys, way I would suggest you do it is you put a line down from the ceiling, because that's probably where you're going to attach it. You're going to put the round pulley. You're going to put the device you're going to lift down here. And if you want to do one, I would start out where you're going to start. And can you see that that's one strand supporting that item? There's basically no mechanical advantage there, but the one advantage is, which would you rather do? Bend over and pick something up, or pull down? Have any of you ever tweaked your back?
Yes.
I would not suggest you ever do that intentionally, because it does not feel, it's not a good sensation. If I want to do two of them, what I would do is I would start up here at this one. Okay, when I did one, where did I attach it to? Bottom. Where do you think I'm going to attach to? I'm going to start at the top, go to another pulley. Can you see that there's two supports there? Okay. This one, where do you think I'm going to attach for 3? The bottom. I'm going to go here. 1, 2, 3. Notice how there's 3 there. Everyone see that? Let's do one more. Okay, Dr. A. Now, if I'm doing 4, am I going to attach it to the top or the bottom? For 3, I attach to the bottom. Where am I going to attach it for 4? Top. Now, I'm also telling you this. Why? Because what are we doing on Monday? A Pulley lab. So we attach it to the top. Go like that. Can you see 4 supports? Now, if this were an actual pulley and we put weight on it, would the rope look like that? No, but on a test, does that make sure that I can tell that you mean 4 strands of supporting it? Yes. Okay, another machine. Another thing we need to worry about is efficiency. Do you get everything out of the machine that you put into it? No. Why? Because of friction. Bicycle is one of the most efficient machines. It's 30% efficient. That means for 100 joules of energy you put in, you get 30 out. Coal plants are only 3% efficient. That means for 100 joules of coal they put in, they only get 3 joules of energy out. And one last thing. Last unit we talked about collisions. You had a lot of fun talking about collisions. In collisions, we talked all the time about momentum. The difference between momentum and energy is momentum is a vector. Energy is not. So in an elastic collision, we hit and we bounce off, and the momentum is conserved. In elastic collisions, perfectly elastic collisions, they hit, they bounce off, and energy is conserved because it's still moving. However, when we have inelastic collisions, where things stick, they have kinetic energy here, kinetic energy here. When they stick, is there any more kinetic energy? So what happens to all that energy? The car crumples. The car heats up. What? You hear the sound of it crunching. All of those things are transformations of the original kinetic energy. Are there any questions on that?